this. What class is next door? You thinking of jumping ship? I don't know what's next door.
Yeah, people find out already. I spent the weekend hoping that
I think so.
Be like, oh yeah, I like expressions. Oh yeah. Because I'm like, the next time it's already due. It's not the next assignment due. Like, I don't know.
So I've decided we're gonna do. Oh, this is not us. I do now. Yeah. Thanks. It's actually where I started teaching.
They still have the well there.
Yeah.
Do they? The well. Says above there. Oh. I used to be just like a little basement room when I used to go there forever ago.
Oh yeah, when I got in with a fake ID.
Oh, wait. I love it there.
I guess I should probably restart the recording. Oops. Let's see here. I'm gonna change this to you guys. Okay, so just a little reminder, because it's been a long time. We've got test 2. We bumped it till the 26th, which I'm kind of sort of regretting, because there's going to be a long time, but it gives us time to review the videos today, or kind of the stuff that you most definitely watched in the videos. And totally watch the videos, and maybe even tried the assignment. I don't know. So I decided we're just going to do more practice problems from section 4.6. There isn't really material. It's just kind of concepts applying exponents and logs. So then I'm bumping the flow duration analysis until Tuesday. Kind of fun, wet stuff. But you can read it, and then we'll do some problems with that on Tuesday next week, and probably some test review, and then we'll start circles. So we'll start trig on Thursday, which is not on the test, and then the test is on the Tuesday, which is only on chapters 3 and 4. And then it's all downhill from here. Chapter 5, do a little bit more trig, final exam review, final exam, pack it up. Pretty good. I know. This part of the term always feels kind of overwhelming to me. I'm like, but I'm just getting to know these guys. Yeah. Yeah, hopefully I'll see you guys again in the winter term, so the second term next year for the data science course, if I still get to teach it. It kind of gets assigned, so we'll see. But I've got a next term, so hopefully I get to keep it. You don't want some stranger, do you? No, that's right. Thank you. So we'll do exponents and exponential and logarithmic models. There's a lot of things that can be modeled by exponents and logs, and one of those that you may or may not have heard of already is the half-life. And so half-life of a radioactive isotope, for example, but half-life, drugs have half-life kind of for potency. A lot of things that decay have half-life. Obviously, it needs to decay because otherwise it would be growing. And so what do we know about decay? Well, decay looks something like this. So at some point, we've got some starting point here. And then at some point, we've got the halfway mark. And how long is that going to take? Right, it's kind of the idea. It's not linear, right? Because we've got this exponential model. And so what we need to do is we need to say, okay, well, what if I know the starting amount, right? We said, all right, let's remember here. Or should we just jump into it? Let's just jump into it. Let's do this example because it's giving us the the equation. All right. No, I want to write it down. F of x is a e to the kt. That's for continuous rates. Right? This is if it's continuous. Or f of x is a still, where a is the initial amount, times 1 plus r, which we were writing as b before, but let's do 1 plus r to the power of t. Really hoping I remembered those right. And if someone could confirm, that'd be cool. But I think I got it. A naught. Oh yeah, so here, this could be ab to the t. Let me just confirm. Wait, oh, the first equation. Oh, so here, a is the initial amount. We don't have to use a, and any initial amount, we usually use a subscript 0. And so maybe that's what's just different notation. It's probably a reason I should watch the videos. If they use different notation, that's okay. Yeah, so they have a starting point, and then they grow or decay depending on what K or T or B is. All right. And you know what? I don't know why I'm so rusty, but I am. So there. I had to make a copy so I keep the other one clean. Okay. And I wanted to confirm. No, it's too long ago. Hopefully I got that right. Can anyone find that? Okay, fine. I'll find it. Where is it? Still earlier. Did you find it? Phew. I was feeling pretty good about it, but then having kind of a cloudy morning, so. All right. At least in this one, we're given the equation, which backs up my original, at least the continuous one. So if we have f of t is 100 times e to the negative 0.036 times t. That gives us some information, right? It tells us that the initial amount is 100. Why? So we know from this equation that f of 0 is 100 because e to the power of 0 is 1. Right? And also whatever the a is in the equation is the starting amount. Clean this up here. Okay. So what we want to find the half-life. So we want to find t when what? When the amount is half of 100. Right? So let me just move this over here. Find t when f of t is 100 divided by 2. Which we know is 50. Okay. So we really want to set this side here, f of t, we want to force that to be 50. And then we want to solve for t. T is up in the exponent, making it, well, part of this chapter, right? Where we have to use logs to bring that t downstairs, right? We use that log property where we can bump it in front. And so we can set 50 is equal to 100 times e to the negative 0.036 times t. 50 divided by 100. So first thing we have to do, we have to isolate the exponential function, right? So I have to move that 100 over. And so I'm going to write it as 0.5 because I'm running out of space here. It does say add pages, so I guess I saw it coming, but is e to the negative 0.036 t. So here we isolate the exponential function. And now we need to take the log to bring that exponent down. Now I'm going to choose the natural log because it's my go-to log, but also I have e in my exponential function as the base, and so I'm going to use log base e, and that makes it a little bit easier. So I've got the natural log of 0.5, and I guess I'm going to add pages like it says. Okay.
Right there, the green, first one right there.
Isolate or take. Because then when I take the log of e to the negative 0.036 t, that essentially cancels. I'm going to write out what the steps are doing, but if you wanted to jump, and I'll show you where you can jump from and to, you're allowed to jump from here to here if you want. In fact, I can take it one step further if I show more work, because the natural log of e to the 1, if we think about it, right, e to the power of 1, e to the power of what is equal to e to the power of 1? Well, 1. And so this becomes 1. So really, if you wanted to, you could show a lot of work, or you're allowed to jump straight from here to here. kind of a leap. And I mean, I'd love to see this step. I don't need to see this step. Right? And I only need to see this step. Because the whole point of taking the log was to bring that exponent downstairs. And now I'm able to solve for t just normally by dividing both sides by negative 0.036. And so I get t is, don't forget that natural log, the natural log of 0.5, which is just a number divided by negative 0.036. Doing a little revolving door switcheroo to clean it up a little bit. And this is a number. And because it's time, we should probably find some approximation. The natural log of 0.5 divided by negative 0.036. I get time is roughly 19.25408835. I want to be careful with time, right? Because this is 19, I guess probably t. I don't know. I'm assuming years. Could be minutes. Could be hours. I don't know. Units. Units of time. But time, we know there's 60 minutes in an hour, for example. And so 0.25 of an hour, we know is 15 minutes, right? And so if you were to rewrite it in terms of hours and minutes, for example, then you'd want to be careful, right? You want to take this 0.254088835 times 60 to turn it into minutes. But I'm fine with just like this because there were no units anyways.
Show all like that whole set of numbers or rounded.
I want to see at least 4. Yeah. But by the time you hit 4, I mean, what's the harm? Nice. Which means that it's going to take, because we didn't have units, that's fine. I don't think, no. So then it would take 19.254 units of time for it to decay to half the amount. Nice. Okay. Any questions about that one? And let me let's do this one then. I feel like the next one is in the wrong. Yeah, it is. It's supposed to be after doubling time anyways. I'll move it. The half-life of iodine 131 is 8 days. So now we know the half-life, okay? And we want to find the annual decay rate. Okay? And so the annual decay rate is going to be, and I'm going to use t because it's time. Now, if you want to use x still, that's totally fine. F of t is a times 1 plus r to the power of t. And we want to find r. Okay. So here, what are we given here? F of how about this? Oops, 1/2 a is a times 1 plus r to the power of 8 days. So time is in days in this case. Right? Because if I know that t must be 8, right? F of 8 must be 1/2 of a, the half-life. So a is the initial amount, right? So a is the initial amount and f of 8 must be 1/2 times a, or a over 2 if you prefer. We also don't really need, you can pick any value of a if you want, right? You could put in 100 and give the half-life as 50, that's fine, right? Or the amount is 50, so just half whatever you want. Or we can just go for it, this part A. F of t is a times 1 plus r to the t. But we said f of 8 is a over 2, which is a times 1 plus r to the power of 8. You may or may not see it, but that a is going to cancel. So it doesn't actually matter what you choose for a, if you want to have a placeholder or if you just use a, because how are we going to solve for this r? I need to isolate this chunk here, 1 plus r to the power of 8. So I need to bump this down, and I need to a over 2 divided by a is 1 plus r to the 8. But a over a becomes 1. So then you're left with 1/2 is 1 plus r to the power of 8. What do we do to get into that base? We need to take the 8th root of both sides, right? So I have 1/2, and maybe I'll just do 0.5 to save us some space. 0.5, the 8th root, and the 8th root of 1 plus r to the power of 8. But remember exponent laws, we can rewrite this as 1 plus r to the 8 to the power of 1 over 8. Right, the 8th root becomes a power of 1 over 8. And then, brushing up on our exponent laws, these two can be multiplied together, which means I have a power of 8 over 8, which was the whole reason I took the 8th root, because now I have a power of 1 here. But this, to calculate, you've got your fancy button on your calculator, which will let you take any root. But if you don't, oops, 1/2, 1/8, you would do 0.5 to the power of 1 over 8. You just confirm that they're the same. So then, put this down. I'm just now having a little moment where I realized last time I used this, I had to mute myself, but I think I'm okay. No one's complained. Hopefully they can hear me. There's 4 people in there, so, although I can't see the chat, so hopefully someone would let me know. Okay, so then I have whatever the 8th root of 0.5 to the power of 1 over 8 I'm old school like that. 0.91700404432. Silver. You want to stack your equal signs, is 1 plus r. I have to subtract 1 from both sides. So then I get r minus 1 is negative 0.08299595568. Negative because it's a decay, right? And the base, if we looked at 1 plus r, 1 plus this negative number is going to be a value between 0 and 1. So b would be between 0 and 1, which is what tells us it's decay, but they're related, right? And so it would decay by 8.2996% per day. Oh, sorry. R is the annual decay rate. Yeah. Annual decay rate is 8.2996%. I dropped the negative because I have the decay here. Gonna wanna add a page. How much will remain in 20 days? This is really, we want to find f of 20, right? So once we have the r, we can substitute that in and we can say, okay, f of t is a times 1 plus r to the power of t. Were we given a? I think we'll just find a fraction of a because we don't have a. But let's rewrite it with our a times 1 minus, it's going to be this, right? 0.91700404432 to the power of t. So we wanted to find f of 20. Did I muck up the units? Because it was in days and the rate is in years. Let's try it. Let's see. We want to find f of, sorry. Undo. F of 20. It's a times 0.91700404432. I have a feeling I need to adjust the days to be in fractions of a year. Yeah. 20 divided by 365. Fine, I'll do it in red. Although I hadn't really committed yet. But we... So 0.91700400432 to the power of 20 over 365. Let's see. 0.91700400432. I get A times 0.995263668 times A, telling me that 99.526% of A would be left after 8 days. Right, or some fraction of A, although I don't get a nice clean number, so. After 8 days, 20 days, where did I go wrong? I need to go back to bed. I didn't do if the half-life is 8 days, I should have less than a half after 20 days. Yeah. Dang it. This, now I have to use red. 8 over 365. Because this has to be the annual decay rate. So T should be in years. There's too much to undo. Thank you. Yeah. Yeah. Find the daily decay rate. Oh, whatever. Do we just start over? Or do we move on? Emily, fix later. I'll fix it. And before I post the notes. Sorry about that, guys. Okay. I will pay more attention to units, even though I don't like units. But in this case, they matter. Have a chance to redeem ourselves, or myself, rather. You guys are doing great. With the doubling time, which is the same, just exponential growth, right? And so the doubling time is the time it takes something to double, of course. And if an account grows by 6% per year, compounded monthly, how long will it take the account to double in size? Now, what we need is from a long time ago. This one. Copy. Where did it go? Here. Oh, that's not nice. I don't like how it switches out my eraser every time I lift it. You guys can't see it, but ugh. Oh my gosh. Ugh. What the heck? Erase. And erase this. Okay. Compound interest looks like this. A is some amount after some time t. A times 1 plus r over k to the power of k times t. And so if the account grows by 6% per year, it's compounded monthly. So then k is the number of compounding periods in 1 year. So k in this case must be 12. We need to start there. R is the annual percentage rate, which is 0.06 because it's 6% per year. A is the starting amount of the account, which is often called the principal in money terms. We don't have A, but that's okay, because what we've seen is, okay, once we kind of shuffle things around, it's going to cancel, right? But A, we can just let it be A. And we want to find how long is it going to take for the account to double in size. So A of t is going to be 2 times A. And we want to find t. Oh. Okay. If I rewrite the equation we're about to use here, A times 1 plus r over k to the power of k times t. I'm going to force the amount to be 2A because it's doubled, starting from A, and then fill in the rest. 1 plus 0.06 divided by 12 to the power of 12 times t, and we want to solve for t. If I need to solve for something in the exponent, t, then I need to isolate the exponential function by dividing both sides by a. When I do that, I get 2a over a, which is going to cancel and just leave you with 2. But then you have, and I'm going to simplify, the 0.06 divided by 12 is small, plus 1. I get 1.005 to the power of 12t. Okay. Now to move that t in the exponent downstairs, I use a log. I am not going to use a log base 1.005, even though you could if you wanted to. But I tend to just use the natural log, right, and just kind of deal with that later. But if you want to, you can use a log base 1.005, but I'll show you why they're the same. So if we take the natural log of both sides, but this I can rewrite as 12t times the natural log of 1.005. And so, but it doesn't cancel anymore because they're not the same base. So I keep it 1.005. solving for t, I'm going to divide both sides by 12 and the natural log of 1.005. And so I get t is the natural log of 2 divided by 12 times the natural log of 1.0.
It's 6 on 5.
Oh, but we had to do 0.06 divided by 12 because you have to do it per month. And hopefully I did that right. Let's see. 0.06 divided by 12. Yeah, it should be 5. Yes. Okay.
How would you do the long way?
So the alternative here is that we could or use log base 1.005. Now what that would look like is you would have the log base 1.005 of 2 is equal to 12t times the log base 1.005 of 1.005, which is just 1. But then here, so then t would be the log base 1.005 of 2 divided by 12. But the change of base formula says that the log base b of a can be rewritten as the log base c of a over the log base c of b. Now, if I let c be e, then I get log base e of 2 is the log base over the log base e of 1.005. But by the change of base formula, this becomes log base 1.005 of 2, which is what you have here. So they're the same. So it doesn't matter which one you prefer. Kind of lost the 12 there, but it's okay. This is a number. Let's use this one. You can confirm that they'll be the same, but we have the natural log of 2 divided by 12 times the natural log of 1.005. And I get t is roughly 11.58131013 years. Yes.
Oh, okay.
Nice. There's kind of a fun rule of thumb. It's called the rule of 72. Have you heard of the rule of 72? A business rule. It's a little fun fact, an LFF. Little fun fact. The rule of 72 says that any investment, so financial investment usually is what we're talking about, will double in 72 divided by R years. So whatever the interest rate is that you're being offered by the bank, you take 72 and divide it by R as a percentage, and that will give you an approximate doubling time. So, for example, says that any amount invested will double in 72 divided by R% years. So it doesn't matter if you invested $1 or $100,000 or whatever. If you want to know how long is that amount going to take to double, you know what double is, then you would take, so in this case, so at 6%, 72 divided by 6, because it's R as a percentage. So 72 divided by 6 gives me 12 years. That's a pretty good approximation of 11.58-ish. All right, kind of quick math, right? Just to have an understanding of kind of what an interest rate would mean to you, right? And so I think that's kind of a fun, useful little thing, right? You're heading to the bank, negotiating. Although I feel like there's not a ton of negotiating, but if they offer you a rate and you want to figure out if it's good, then you need to figure out, okay, well, how long do I need, or how long can I wait for it to double, right? And then that's the rule of 72. So they offer you 4%. How long would it take $1 to double? 72 divided by 4, 18 years. Can I wait that long? For $1 to go to $2, I guess. I don't know. But I like to introduce that one because I think it's a useful math tool, but it is doubling time, right? And you can derive it using logs and things like that, but kind of fun. Okay. A population of fruit flies doubles every 10 days. We want to find the annual growth rate. Should I give you a moment to try it? Let's do that. Have a moment to try it, because we've already done it, sort of. I'll pause the recording though. It's up again. Okay. If it doubles every 10 days, we have something like f of t is a times 1 plus r to the power of t. Now, what I'm struggling with is that t is in days, but I want to find the annual growth rate. So do I need to convert the t to years? Question. No?
Well, didn't we just find R and then convert it to years?
I wonder if it makes a difference. I checked, and last year I did not convert the days to years. So maybe this year I do. Let's try it. 10 days. Let t be in years. Oops. Oh, I see what you mean. Like find r. Convert it. That would work too. Let's try it. Try it side by side, maybe. No, too much work. Okay. A population of fruit flies doubles. So I get 2 times A is A times 1 plus R every 10 days. So T10 divided by 365. It always feels weird when you're first starting out to just let A be A, right? And just kind of hold it, but it will cancel out, right? And so we get 2A over A, which I'm not going to write, is 1 plus R to the 10 over 365. So you can use just 10, and then you would divide it by, or then you'd multiply the R by 365 when you find it later, or I'm gonna let T be in years, and then R will just be in years. Yeah. So then 1 plus R to the 10 over 365. So I need to take the 10th root and to the power of 365. So this becomes 2 to the 365 over 10 is equal to 1 plus R to the 10 over 365 to the power of 365 over 10. Because that's going to cancel to 1. 365 divided by 365 is 1. 10 over 10 is 1. And so this kind of made a mess. 2 to the power of 365 divided by 10. It's way too big, I guess. Does that make sense? 2 to the power of but I get 9.7184 times 10 to the 10. It's huge. Kind of makes sense. Is equal to 1 plus R. Yeah, I mean, it kind of makes sense. Usually the rate is between 0 and 1, but minus 1, I get 9.7184016, oops, times 10 to the power of 10 is equal to R. But that's huge.
Well, no, because 36.5 is the 10th of the year. So if you take 2 to the power of 36.5, it's 9.71. So
Say that again.
correct.
Okay. Say it again.
So 36.5 is a 10th of 365. So
Yeah.
you take 2 to the power of 36.5. It doubles every 36.5. Which is 365. So you get the same answer.
Phew. Thank you. It is fruit flies. Yikes. I'm just kind of scared by this as a percentage. 9.7 times 10 to the power of 10 times 100. Yikes. 9.7.
Minus 1.
Yeah, just no. It's like, yeah. Yeah, it didn't, well, it did something, but not really. All for the gram, right? I assume. No. It's all for the gram. The Instagram. No. Per year. So R is 9.718 times 10 to the power of 12% per year. Yikes. Gross.
Why did the power of 12?
Because I multiplied by 100.
Why?
Because this would still be R as a proportion, so divided by 100. And so to get the percentage, multiplied by 100. But this is the one we're going to use in our math. Right. Okay. Annual growth rate, gross. How large will the population be in 20 days? Well, if it doubles in 10 days, should roughly quadruple, right? Double in 20 days. So let's see here. We want to find f of 20 divided by 365 is a times this huge number, bring it back to a proportion, plus 1. 1 plus r, can I just do this? Because it's too big. Anyways. To the power of 20 over 365. So I have this value. I can take it to the power of 20 over 365. If I get a times 4. Which is 4a. Double twice in 20 days. So that checks out. Right, if the doubling time is 10 days, then in 20 days, we expect it to double twice. What about how large will the population be in 45 days? Now, 45 isn't a nice kind of multiple of 10, but it would have to double at least 4 times, right? 10, 20, 30, 40, and then a half, right? Roughly. So we can still do that math. F of 45 over 365, whatever a is, times 1 plus, and I'm gonna say I stored this in a. I haven't yet, so I should. 2 to the power of 365 divided by 10. And I'm gonna write stored in A. That's more of a note to myself. And if you want to indicate to me that you stored it in your calculator, that's what you can do. Then you can use stow A or B or C or whatever you want. So now I've stored it. 1 plus shift recall A to the power of 45 over 365. 22.62741.7A. Did I do that right? Yeah. So it has to double. Two times 2 times 2 times 2. 16 and then some. Somewhere between, right? If we think about where 45 is in relation to the doubling time, if the doubling time is 10 days, then it's going to be somewhere between doubling 4 times over or 5 times over. And so if I go 2 times 2 times 2 times 2, I get 16 days, or 16A. And then if I double it again, times 2, 32. Which is between 16A and 32A, which is 4 doubles, if that makes sense, and this is 5 doubles. Here, I'll do 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2. Or 2 to the power of 5, 2 to the power of 4, if you prefer. But I actually like the 2 times 2 times 2 times 2 in this case. Nice. All right. Tricky, those fruit flies, the huge rate. Questions about that one?
So would the answer need to be an answer exactly like yours? Because I got 23.6274. I checked it over a couple times. Kept on getting the same.
Oh, maybe I did it wrong. Did you keep all your decimal places?
Yeah.
And did I add it to 1? Maybe that's a better question. 1 plus recall A. Oh, I think it's not 1 plus, is it? I have to do 1 minus because I just did this in my store A. Sorry about that. My bad. A minus 1 plus 1. Oh, it should be this. But I don't need this. That's my problem. So this is, no, because I already, because I stored this 2 to the 365 over 10, which is 1 plus R, but then I was adding 1. So let's try it again here. 2, start with 2 to the 365 over 10, start fresh. And then I want that to the power of 45 over 365. I still get 22.62. What are you guys getting?
No matter what I say, I can't. Oh, there we go. Now I got 22.6. I'm getting like, does that +1 really matter with the number?
It'll kind of rear its head.
I got 22.6.
Yeah. So yeah, it will, but only in a minor way. So I think I'm ready to commit to 22.627417. Which is still between 16 and 32. So that's good. This one, I feel like this one I didn't actually use. How about this? I used I feel like should recall a -1. Okay. Let me just check this here. Or maybe I don't do this. Am I going to get? Oh man, shift recall A to the. Yeah, so it looks like I had used the right value, but then had written 1+, but
1+ origin.
yeah, but it was just, it's all good. If I just change it to store A. Keep track of that.
I don't understand how it makes such a big difference. It's the 10th power. It's such a big number.
I know it's.
One to the answer.
Yeah. But
like, would we still get it right if it's off by 1 in the answer?
Yeah. I mean, yeah. Because, but the thing is, 1 in terms of R is actually 100%.
Oh.
So that's why it's making a big difference. But even relative to like this huge number, this huge rate.
Oh, so that big number is percentage.
Yeah. Yeah.
Oh, okay, that makes more sense.
So even, yeah, so even the 1, if it's missing, you're missing like a multiple of 100%. So that's why it's making a big difference. But yeah, at this point, if you kind of got to here and then, well, even I bungled it and I wrote 1+ store A, even though store A was the 1+ R already. So that's fine. Not too picky about that kind of stuff. As long as you're showing me what you want to be doing. Okay. Problem solving. What's the next thing? Newton's law of cooling. It's kind of fun. So Newton's law of cooling says that the temperature of an object, T, in surrounding air with temperature Ts for the surroundings, will behave according to the formula T at time T. So the temperature at time T is the is A, which is no longer the starting amount, but it's just a constant. And so A times e to the kt plus the starting or the surrounding air temperature. So T is time, and A is a constant, which we find by the initial temperature of the object, and K is a constant. And it's the continuous rate of cooling. I was about to try to do a problem. We don't have a problem yet. Here's a turkey. Let's see here. And I'll move the, I had to add a clarifying note there. Or maybe I didn't. Oops. That's, after so a turkey is taken out of the oven at 165 degrees and placed in a 70-degree room. Celsius, no. After 10 minutes, it's cooled to 150 degrees. What will the temperature be in 30 minutes? And I clarify after removing it from the oven. So we know that T of T, let's start there. T of T is A times e to the kt plus T of the surroundings. We're also given T of the surroundings. The temperature of the surroundings is 70, right? So if you have a turkey and you pull it out of the oven, we know it's going to be hot, and then you let it rest on the counter or whatever, and then it's going to cool off, right? The temperature of the turkey is going to cool off and decay. And so then, but it's not going to decay past the room temperature, right? I mean, that'd be pretty weird if it did, the surrounding temperature. And so the surrounding temperature is 70. Yeah. And we're also given that the initial temperature, so of the oven that it came from, presumably it's the same temperature as the oven, T of 0 is 165. I'm going to let T be in minutes, because after 10 minutes, it's cooled to 150 degrees. And all the rest is in minutes, so I'm safe to just use minutes. But the rate would be per minute as well. So after 10 minutes, it has cooled to 150 degrees. So T at 10 is 150. Okay. We can start by solving for A, because from T of 0, it has to be 165. So 165 must be A times e to the power of 0, which is 1, plus the surrounding temperature, 70. So 165 minus 70 is 95. So A is no longer the initial temperature because we need to adjust for the surrounding temperature, right? But that would be your first step in kind of picking away at this formula. Then what we're going to do, I'll say here, use T of 0 to find A. So now we have A is 95. So let's see what we have here. We'll take a step back. T of t is 95 e to the k times t plus 70. So now I'm going to use the next check-in point at t of 10 because I know that that has to be 150. So 150 is 95 e to the k times 10 plus 70. So now I'm going to say we're going to use t of 10 equals 150 to find k. A multi-step process. So here I have k in the exponent, which means I need to isolate the exponent. And if we remember, right, first I have to subtract 70 from both sides, and then I can divide by 95. And so I get 150 minus 70 is 80, is 95 e to the, I'll do 10k just because it's a little bit cleaner. Hey, I'm just realizing I don't know what time it is. Hammer time. Okay. And when do we go till 9:50? In a haze today. Just can't. 80 over 95. What I'm going to do is I'm going to keep it as 80 over 95. Your calculator simplifies it to 16 over 19, hopefully. So maybe we can use that. But you're either going to store the value or use the exact value, right? And so because we want to find the exact value for k, and so I'm just going to keep it as 80 over 95 is e to the 10k. If I have e as my base, I'm going to use log base e. So the natural log of 80 over 95 is, can I jump to 10k times the natural log of e, which is 1? 10k. So then k must be the natural log of 80 over 95 minus, divided by 10, sorry. So if I take the natural log of 80 over 95, divide that by 10, k is roughly negative 0.01718502.569. Per minute. I wonder how big of a difference it would make if I used some sort of rounded value of 80 over 95. 80 over 95 is 0.842105. Try using a rounded value. What I suspect is it's going to make kind of a mess. 0.842. Kind of run out of action after 0.842 is 10 to the k. The log of 0.84, oops, well, it helps if I enter it right. 0.842 divided by 10. Not too much. not too different. They are different, but I think I'm okay with that. Okay, so now, and this was all doing this. So what do we have? Therefore, T of t is 95 times e to the negative 0.017. Kind of go until I run out of activity. So either way, I would probably stop at 4 decimal places here. If I run this up to 2, I've kind of zipped this all up, right? 1 followed by an 8 is going to round to 2, but same here. 1 followed by 9 is going to round to 2. And so either way, t plus 7. So now I have the equation for this turkey, the cooling. And now I can plug in any value of t and solve for the temperature, which we're going to do. What will the temperature be in 30 minutes after removing it from the oven? So in 30 minutes, this wasn't part of A at all. It's just finding the equation. Now we can use the equation. T of 30 is 95 e to the negative 0.0172 times 30. I am going to store it, the exact value, just for a little comparison. I did the log of 80 over 95, divided by 10. Store that. But I'll use the rounded value here first. Negative 0.0172 times 30 e to the power of that times 95 plus 70. I get 126.7058223 degrees Fahrenheit. Now, what if I use the exact value for K? Let's see if it makes a difference. Shift recall A times 30 e to the power of that. Oops. E to the power of that times 95 plus 70. 126.73, blah, blah, blah. So it's not. Nothing major, all good. So that would be the temperature after 30 minutes. And how long will it take to cool to 100 degrees? 100 degrees. The next one is so morbid. I know, we get our CSI on. T of t, we're going to force it to be 100. Is 95 e to the negative 0.0172 times t plus 70. Now, I'm going to solve for t by isolating the exponential function. And so first I'm going to subtract 70 and then divide by 95. And I get 100 minus 70 is 30 divided by 95 is, and I know you guys love rounded values. Let's go for it. I'll try to use the rounded value. I can't stop though. It's my problem. 8. This is rounded just for you. Because we've kind of lost it all. If we're using a rounded value for k, then we can keep rounding. Might catch up with us. Solving for t, I need to take the log. I'm going to choose log base e because I have e as the base, so it makes sense. The natural log of 0.3158 is the natural log of e to the negative 0.0172t. Natural log of 0.3158 is negative 0.0172t. Solving for t. Natural log of 0.3158 divided by negative 0.172. Yeah. It's nice because these types of questions, you know, you have to build the equation and you have to use logs, you have to use exponential functions and all that kind of fun stuff. So they are good ways of kind of testing all the things. But you got to keep your wits about you. Usually I have kind of quick 1 or 2 mark questions where it's just do this, do this, do this, do this, kind of how we started in the chapter. And then some bigger mark questions like this, right? As long as you follow through, like if you, for some reason, bungled finding the A or something very early on, as long as you follow through with whatever you told me A was going to be, I mean, how are you supposed to know that you did it wrong, right? So as long as you follow through and you use that same value of A that you found, that's fine, right? Just kind of follow through with whatever. Even if you get here and you say, I am completely stumped for how to find K, but you know you need K later on, then just say, I'm going to use a reasonable value. I'm going to let K be, so K is always negative because it's cooling, right? So you have to keep track of that. And it's usually kind of a small number like this, right? Let K be negative 0.01, and then just keep going with that. And I get T is roughly 67.01431263 minutes. Just over an hour. Could also figure out how long it takes it to reach room temperature, 70. But maybe you don't want to serve it at room temperature. Kind of defeats the purpose. Maybe, I don't know. Okay. Questions about that? One. So just over an hour and 7 minutes.
What?
Yeah.
Yes.
Really?
Yeah. Honestly? Yeah.
Her voice. Yeah.
So she can't see, everyone's gonna smile on their face.
I'm rattled right now. Just putting this off all week so I can talk or finish this.
They still do it.
Yeah.
That research plan. Is she available for
Yeah, she's available for 8 hours. What research plan?
Negative. Negative.
Research. Like, why can't we just do our thing and then? Which is, I get more important stuff to communication. I don't care, I'm gonna do less, do everything else more important and then do communication last minute.
I'm sorry, yeah.
Oh, dude,
I added one more left.
Nice. Good, good, good. Yeah.
Yeah, question. Very different answer. Why you were doing the same and now we're talking about this.
Because it's not using the exponential function.
Yeah, like they always do it a different way, but the
Yeah.
answer is way different.
Sorry, I just took your phone.
I was working on these questions during the homework.
Can you send this to me?
Used me a lot. Yeah.
Yeah. So I will say it doesn't really know math usually.
Yeah, exactly. Yeah,
It's
I've
still
noticed that.
learning math. And yeah, it's yeah, I think it's skipping the exponential part of it. Yeah. Yeah. I wonder if you could add something into the prompt saying kind of the exponential function or something, kind of prompt it that way. But yeah, I know when AI, just broad terms, kind of came out, hit the scene, it would produce very reasonable looking answers, but the math was just like, it was like, and 14 minus 2 is 20. And so it was like, no. Yeah, because I mean, I'm thinking about ChatGPT, which I played around with quite a bit. Because ChatGPT especially is just a text predictor. So it would say, okay, well, 14 and then minus 2, but then a really common number is 20. And so it would just kind of predict what would happen next. It's smarter now, obviously, but it's, yeah, kind of tricky that way. But yeah, just kind of funny because it looks completely reasonable. And then it's like, here's a reasonable answer. And if you're not paying attention, doesn't work. But it is smarter now, obviously. But I wonder if it's just missing the kind of exponential prompt or something. How about this one? Or I guess I should check what time it is. And that's it. It is. If I keep my pace up, it is. But maybe it's a nice one to use. For review. No, let's try it. We'll see how far we get. Because there's still orders of magnitude and things to talk about, so that's fine. Dead body is found. If I could make the CSI screeching noise, I would. Its temperature was 85 degrees when found. After 30 minutes, its temperature was measured again to be 82 degrees. So you can see how We don't know the initial temperature, of course, but we now have temperature measurements at 2 time points, which is obviously what they would need to do. You can also measure the surrounding air temperature is 60 degrees. And then what we're going to do is we're going to backtrack it to when did this person die if we assume that the body temperature at the time of death was 98.6 degrees, which is kind of a body temperature. So, what are we gonna do? I would say the easiest thing to do might be to let the time when it was found be time 0, right? We're gonna find a negative time for when it was a higher degrees, but maybe that's okay. Because, or what's the alternative? We can let this be T of T1 is 85, and this is T of T1 plus 30 is 82. Whoops. Kind of 2 different ways. Let's do it that way. The surrounding temperature is 60. So I have T of T1 is 85, which is A times E to the KT plus TS. I know the surrounding temperature is 60. Oh, this is T1. I also have T of T1 plus 30 is 82. A e to the K times T1 plus 30 plus 60. Okay. Now, my goal here is to solve for A, which is the best way. Let's set these. My go-to move would probably be to set these both equal to 0. I want to set them to be equal to each other eventually, right? But I need kind of a gateway to do that. And so let's try it. What if I set T of T1 and T of T1 plus 30 equal to 0? I can do that by subtracting 85 to this side and 82 to this side. So then I get A e to the K T1 plus 60 minus 85 is minus 25 is equal to 0. Oops. And I'm going to have the equal 0 link there. You don't have to, but then I'm going to subtract 82 from, so 60 minus 82, and I get, oops, A e to the K T1 plus 30 minus 22. Guess the A is gonna cancel. Nice. So now, because I set them both equal to 0, I can rearrange some stuff. Right? And I can do something weird. Like, what weird thing can I do? I can do a lot of weird stuff. What's the best thing? A e to the k t 1 minus a e to the k t 1 plus 30k. Expanding that inside is equal to negative 22 plus 25, 3. I didn't like where this headed. Where did I go wrong? Maybe you just need to stay the course. But how? Yeah. Let's try that. Let t1 equal to 0. That'll simplify things. A e to the 0 minus a e to the 0 plus 30k is equal to 3. E to the power of 0 is 1, so I get a times 1 minus a e to the 30k is 3. I can pull out a common multiple of a times 1 minus e to the 30k is 3. Which means the k needs to go away.
Why isn't that 98.6 the 8?
Because it's not the yeah, maybe that's where we start. Oh man, today is not my day. Sorry guys. Should have canceled today's tail. I don't know. I just feel like, yeah, I just can't get it together today. Okay. How about this? Because I suspect I'm overtime. I'm gonna start here.
The way that I did it was just t over 0, or t of 0 equals 85, and just solve for it without combining it.
And you get 25. Because 85. That's nice. Wonder if we can do it both ways. Yeah, either way, I'm gonna have to rework this in the privacy of my own office. Or something. I'll post the solutions and obviously we'll go through it on Tuesday, but I release you. Man, what a day. Okay.